We are still talking about dynamic programming, and I'm going to solve another problem using dynamic programming. This is in fact two problems closely related to each other. That's why I'm explaining both of them together. Subset sum and knapsack. So what is the subset sum problem? Assume you have a set of numbers and positive numbers, a1 to an, and you also have a target number t. We wanted to know if it is possible to find a set of these a set of these numbers, that the summation of them are exactly equal to this target number t. Let me actually give you an example. Assume I have four numbers, 1, 3, 8, and 5, and 15. And we are going to look for a set of these numbers that the summation of them is equal to 19. The answer here is yes, and I can find a set of these numbers. And what are those numbers? The numbers are going to be 1, 3, and 15, right? Be careful, in this problem you cannot repeat any of these numbers. It's just like you have just one number from each of them in the sequence. There might be actually some repetition in the sequence, but you cannot repeatedly choose. For example, if maybe a1 and a2, both of them are 1, but you cannot actually choose for example 3 1. If there are only 2 1, you can only take 2 1s. Okay. And one more example, it's not always, the answer is not always yes. For example, if in the same example I have t equal to 20, it's not possible to find any set of these 4 numbers that the summation of them will be equal to 20. I can extend this problem and get another version of it, that I wanted to find, I have this given target number t. I want to find a set of numbers from that given set of numbers, that the summation of them is, I want to actually losing that constraint. I don't care that it is going to be exactly equal or not. It should be less than or equal to t, but I wanted to maximize the summation. Okay, so if you just put this constraint, so in this way you can actually just say that whatever is the value of t, you can always, the answer is going to be yes, because you don't take any number. No, I'm just changing the whole problem and saying that I want to choose a set of numbers that the summation of them is less than t, less than or equal to t, but I wanted to maximize that summation. Okay, so in that case, in the previous example that I have, the set of numbers 1, 3, 8, and 15, and the target number t, so the optimal answer is going to be take 1, 3, and 15. The summation of them is going to be less than the summation of these numbers is going to be less than or equal to 20, and this is the maximum number that you can actually get. So actually knapsack is something very similar to the extended version of subset sum. The knapsack problem is saying that I have n items, and there are 2 numbers associated to these items. There is a value and there is a weight. So the intuition here is that assume you have a knapsack, you wanted to fill this knapsack with some items. The items have some value and they also have some weight. Your knapsack is not going to take more than some specific weight. Let's just call it W. I wanted to gather as much value as I can, but so that I can actually put all of them in the in the knapsack, I can carry all of those. So the weight of all of those numbers are going to be less than, the summation of the weight is going to be less than W, but I wanted to maximize the value of those objects. So here you can see that I have basically two factors in this problem. So I'm going to explain the original problem, the subset sum problem. And then I will talk about the knapsack. Actually, if we know how to solve the subset sum problem, we can extend that solution and solve the knapsack problem as well. So the original problem was that I have n positive integer number and I have a target number t. I wanted to see that if I can find a subset of these numbers that the summation is equal to t. So the naive algorithm that first comes to mind is, okay, think about all the possible subsets. Just consider all possible subsets, take the summation of all those subsets, compare it to the value t. If any of them is equal to, the summation of any of them is equal to t, you find the answer, and that's going to be the set of numbers that we want. Of course, this algorithm, this naive algorithm is not going to be good. The number, if you have n items, the number of subsets is going to be 2 power n. And it is exponential. It's, in fact, you need to calculate the summation of those numbers. So in total, the time complexity of this algorithm is going to be n 2 power n, which is not good, of course. So we wanted to find a better solution. So here the idea is very similar. I mean, the first idea that comes to mind is to search in this search space that we have is very similar to the interval scheduling problem. Remember, in the interval scheduling problem, we try to just take consider each job and say that, okay, I'm going to take this job or no. If I take this job, all those that have conflict cannot be chosen, and then among the rest of them, what is the optimal answer? All right, I'm going to do exactly the same. I'm trying to, when you are, I'm thinking about finding the recursive relation, I will first think about the exhaustive search, then try to find some structure over the subproblems and try to find some repetition between the smaller subproblems that I will solve in this recursive tree, in this exhaustive search. Okay, so here again, I'm going to actually think about it in this way. At the first, I would say that I wanted to find a set of numbers that the summation of them is equal to t, right? And I have access to all the numbers. Then I would think that, okay, am I going to take the first item or no? If I'm going to take the first item, so it means that I have taken A1, okay? So I wanted to know that among all the items from number 2 to n, A2 to AN, is there any set of these numbers that the summation of them is going to be t minus A1? Because I have already taken A1, right? I need to subtract this from that summation. If I'm not going to take A1, you are going to actually say that, okay, give me the answer. I'm not going to take A1. A1 is not in the optimal answer. Okay, find a solution for a problem that has all the numbers from A2 to AN with the summation equal to t. I just decided about t. I just decided about the first item. Either I'm going to take that item or no. If I take it this way, if I don't take it this way. Okay, and then again, you actually just repeatedly do the same. For example, you decide about, here you are going to decide about A2, and here you are going to decide about A2 again. Either you are going to take A2. If you take A2, So it's just like you are going to find a subproblem that it has all the numbers from A3 to AN, and the summation of T minus A1 minus A2. And another subproblem that you need to solve is that you have already taken A1, but you are not going to take A2. Okay, so it means that you are going to solve a problem. Again, all the items from A3 to AN, but the summation that I have is going to be T minus A1. I took A1 and I decided to don't take A2. Again, you can actually just extend all these branches here as well, that you decide about A2. You didn't take A1, you didn't, if you are going to take A2, so the problem here is going to be find an answer for all the items from 3 to N, from A3 to AN, and you already took A2. So the summation, the target number that remains is T minus A2, and here just I didn't take A1 and I didn't take A2. Find an answer among all the numbers from A3 to AN with the summation equal to T. So if I actually expand this tree completely, you will see that this is going to be the complete search that I need to do. There are a couple of actually things about this idea. Unlike the interval scheduling that I could sort the jobs based on some, for example, the sorting time, and if after some time you are actually discarding all the jobs starting or ending before that time, starting before that time, here I cannot discard the items. These are exactly just a subset of items. All these items are completely disjoint. You can actually take an item or don't take an item. It makes it more difficult than the interval scheduling. But still there is something interesting here. The first thing is, in addition to the set of items, we can see that each of these nodes, in fact, is a problem of the sum problem, right? But it has different actually parameters. All of them are going to have different parameters, and I have two main different parameters. One of them is that target number, the other one is the set of items that I'm working on. Okay, so you have T or T minus A2 or T minus A1. So that number is changing, right? That target number is changing. So this is one parameter that will change. And in addition to the set of items that you can choose from. But I can do some structure. I'm going to actually define some structure over these two different parameters that I have. The first thing is that instead of thinking about all subsets of the items, I have n items, right? If you are going to think about all subsets, it is going to be 2 power n. I don't want to go that way. Exactly the way that I fixed this searching here, that I started from item 1 and I'm not actually jumping to, for example, item n, item I don't know, 15, somewhere else. I'm actually following some order, because it doesn't really matter that which order you are thinking about, if you started from the last item or if you started from the first item. But still, I'm going to just define some structure over these subproblems. I am going to say that you can choose all the items from 1 to n, okay? Or you can choose, here I'm actually changing it to all the numbers, all the items from index 2 to n. I just discarded one. All the items from 2 to n, and then from all the items from 3 to n. So the rest of, I'm going to actually just create a smaller subproblems by fixing n and saying and telling you that you have a choice to choose from 1 to n. It doesn't matter that you are choosing all of them or none of them, in fact. But you have this choice. You have access to all the items from 1 to n. You can actually take them or no. For example, if you have this case of 3 to n, it doesn't mean that the optimal answer that you find for this node is going to definitely take 3 or not. It's just telling you that from the item index 3 to n, you have a choice. You have a choice that you can choose any of these items. Okay, so I just fixed something about these parameters. The first parameter is which is the number of items that you have. So it's going to be from, if it is 1, it means that you have access to all the numbers from 1 to n. If it is 2, it means that you have access to all the items from 2 to n. If it is 3, it means that you have access to all the items from 3 to n. If it is I, it means that you have access to all the items from I to n. Okay, so it means that I don't need to think about all the subsets of items. I fixed it and saying that from 1 to n, you can access to all of them. But I don't care that which one you are taking. From 2 to n, you have access to all the items. Although I don't care that how many of them or which of them you are going to take. So in this way, I actually reduced the number of subproblems a lot. So it means that if you have n items, this parameter, you have in your subproblems, you have 2 parameters, right? This one and this one. This parameter is going to have only n options, okay, from 1 to n. The other one is t. So, and for t, you can see that you can have it as t minus a1, t minus a2, t minus a1, a2. So if, for example, t is 100, all the target values from 0 to 100 are going to actually happen in your subproblems. It is a chance that you, for example, a1 can be 15, can be 50, can be 80, right? So this parameter, the second parameter in your subproblems can be any number from 0 to t, whatever is the value of t. So I fixed, in this way, I find some structure. I have some subproblems that has 2 parameters, I and the other one L. That I can be from 1 to n. It's actually talking about the items, the indexes of the sequence, and L is talking about the target value that can actually vary from 0 to t. Okay, so the rest of the thing that I wanted to actually write is just finding a recursive relation. So let's just write that one as a, let's just give it a name like sum for I and L. What is the recursive relation for this? So it's just like for each of these boxes, each of these nodes, each of them are going to be one subproblem, right? What is the recursive relation? Let's actually start it from the first one. The first one tells you that you have access to all the numbers from 1 to n, right? And the target value is t. So either I am going to take A1 or I'm not going to take A1. So it's just two actions, two subproblems. So if any of these are going to have the answer true, you are saying that yes, the answer for this subproblem is also going to be true. But how can I write this recursive relation? For the very first subproblem, the subproblem is that sub sum for 1 and t. These are actually exactly two parameters for my problem, right? All the numbers from 1 to n and the target value equal to t. This is going to be that if this one is true or this one is true, the answer is going to be true. So it's just like the answer is coming from two cases. This subproblem will be you are taking A1, right? And so the target is going to be t minus A1. So it's going to be sum, let me clean here, erase here, sum of from the item 2 to n. I don't have access to the first item anymore. And what is the target? The remaining target is t minus A1. If the answer here is true, this is going to be true as well. Or subsum for 2 and t. I didn't take A1. So the target is still t, but I can only take some item from all the items from 2 to A2 to AN. If any of these two is true, this one is going to be true. So it's just like you are taking OR between these two actual cases. This is going to be your recursive relation. So if I wanted to actually write it, this is going to be like this, that all the subproblems that I defined was this, that for all different values of I and L, I is between 1 and n, all the objects from I to n, and L is going to be all the values between 0 and t. Okay, and basically each of these subproblem is telling you that this is going to be yes or this is going to be true if there is a subset between all the items from I to n, nothing else. You are not going to access to those indexes before I, which the summation is equal to L. And the optimal answer for the original problem is going to be here, which means that you have access to all the items from 1 to n, right? And the target is supposed to be t. And this is the full reoccurrence relation for that. That for each value, each subproblem of I and L, either you are taking the item A sub I or you are not taking it. If you take it, it means that the value of subsum will actually increase. It will be I plus 1, because it means that anyway you have decided about the ith item. Either you are taking it or no. You are not going to actually use it anymore. So if you take it, the next subproblem is going to be I plus 1, and the target will be updated with L minus A sub I, or you are not going to take it. So anyway, you are not going to take it, so the items that you are going to have access to is going to be from I plus 1 to n, and the target is still L. I think the best way to explain, if you haven't got the idea, the best way to explain it is over the previous example that we had. So the table, these subproblems that we have defined, needs to be stored in some table, right? I is going to be between 1 and n. L is going to be between 0 and t. So I need a table of size n to t. In the very first example that I showed you, the set of numbers was 1, 3, 8, and 15. So I have 4 numbers, right? And let's actually just call them the same order that we have. It doesn't really matter that if you sort them or not. Unlike the case of interval scheduling, I don't really care if they are sorted from the smallest to largest or they are just randomly. So I don't care. But in this case, they haven't sorted. It's just, it happened. I didn't meant to keep them ordered. So let's just call them from A1 to A4. And t, the target value that we are looking for, is 19. So I'm going to have a table. This is going to be that table subsum, that lookup table that I'm going to keep, right? Which is n to t. That's the size of it is n to t. In fact, t plus 1, because we are considering from 0 to t. Okay, so the final answer that we are looking for, let me actually just write down that the original problem that we had was subsum from actually 1 to n with the target value equal to 19, right? So in fact, in this table, what I'm looking for is this cell. How I'm going to actually fill this table? The very first thing that I know is if the target is 0, basically if you don't choose anything, the summation is going to be 0, and so the answer for all the cell in this column is going to be true. So basically I can just put true here. This is the very first thing that I can solve. After that, remember this I is going to tell you that you have access to all the items from I to n. Okay, so when I is small, the problem is bigger because you have access to all the items. When I is equal to n, the problem is smaller. So it is going to be, I'm going to fill the table from the last row to up. Okay, these are going to tell me that in this row, I'm going to solve the problem for the case that I only have access to the last item, A4. Okay, and I can simply solve this. I can go through all the items, all the cells in this row, in the last row, and fill it. I know that I only have access to 15. So if the target is t, for example, the target is t, and the only item that I have is 15. Can you find a set of these items, 15, that the summation is going to be equal to 1? No. So basically for all the numbers in this row, all the cells in this row, the answer is going to be false, 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 except the case that the target is in fact equal to an, which is going to be this case. Right? So except this cell, everything else is going to be false. If, for example, the last item was something like 22, and your target is 15, right? So all of them will be false. In this case, the last item is 15, which is smaller than 19. So one of them is going to be true. The rest of them, all of them, is going to be false. Okay. After that, I'm going to complete this row. This row is telling me that I have access to A3 and A4, which is going to be 8 and 15. How I'm going to solve, fill this row? Again, I'm going to fill it from left to right, because these numbers, are the target number. When it is smaller, the problem is going to be easier to solve, right? So when you are actually solving this cell, you are looking at two cases. So what is that cell? That cell is sub sum of 3. You have it means that you have access to the item 3 and 4, and the target value equal to 1. The recursive relation basically tells me that it's going to be true if any of these two cases is true. Sub sum for 4 and L minus AI, which is going to be L minus 18, 1 minus 18, 1 minus 8 is going to be 7 minus 7, or subsum of 4 and 1. This one is going to be false. I already have that. And what is this one? You can see that I don't have something corresponding to this, because one of them, the target number became negative. You can either actually created a cell for, some cell for this. But anyway, if the target is negative, it means that you are going to take some bigger number. So it's not possible. So if the target is negative, you should always know that the answer is false. You are going to take the summation of some positive number that the summation of them are going to be negative. So of course this answer is going to be false. When you are writing the code or pseudocode for that, you can just simply keep track of this special case, that if the target became something negative, it is always negative. It is always false. So this is false. This is false. Of course, the answer for this one is going to be false. Similar to that, this one is going to be false. This one is going to be false. So this actually coming from either this cell or again the target is going to be 4 minus 8, which is going to be some negative, right? So all of these numbers until 8 is going to be, all of these cells until 8 is going to be false. So when I reach to 8, this cell, which is going to be subsum of 3 and 8, it is telling you that you have access to all these items from index 3 to index n, and the target is 8. What are A3 and A4? These are going to be 8 and 15, right? So the answer for this one is going to come from subsum of 4 and 0, or subsum of 4 and 8. I'm actually just following this relation. 4, I plus 1, and L minus A sub I, which is A sub 3, which is going to be 3, or I plus 1 and L. This one is here. This is false. So this one is here, which is false, but the other one is here, which is true, right? And the answer for this one is going to be true. And it actually makes sense, right? You have two items, 8 and 15, and you wanted to get the take sum of them to which is the summation of it is equal to 8. Of course you are going to take A3, which is equal to 8, and this answer is going to be equal to true. The answer is true for this one. And the rest of this cell is going to be false if you, actually, for example, for this one, for 9, the answers for the cell 3 and 9, this cell in the table is going to come from these two cells. 4 and 1 or 4 and 9. If you think about these two cells, 4 and 1 is here. 4 and 1 is here. 4 and 9 is here. Both of them are false. So the answer, of course, here is going to be false. Or for example, for this case, you are looking at either this answer or 4 and 2, which is here, which is again false. So the answer here is going to be false. So you can go ahead and fill all of these cells. As you can see, I'm actually filling the rows from bottom to, from this way, from the largest to the smallest, and from left to right. And I'm just following this formula, this recursive formula. So what I wrote there is actually here. This is the bottom-up algorithm that I wrote. I already actually in the slides have written the top-down algorithm for you as well, with the lookup table and without the lookup table, everything. But anyway, what I have explained on that table is exactly this algorithm. So what is the time complexity? It is clear that the time complexity is going to be O of n to t. The reason is that you are filling such a table, and for the cost of calculating the answer for each of these cells is just you are looking at two other cells. Whatever is the answer from them, you take OR between them, and this is going to be the answer for the next cell. So the computation for each cell is constant. I have a table of size n to t, and so the cost is going to be n to t. So there is something about this type of algorithm, which are n to t. You might actually say that this is going to be polynomial, but we don't call them polynomial time algorithm. We call them pseudo-polynomial algorithms. The reason is you have this term t in your time complexity, which t is going to be the input of your algorithm. Not only you have n item, a sequence of n item, you have another parameter t, and that parameter t can be crazy big. So if you have t is equal to 1 trillion, the problem is going to be really difficult to solve. And the reason is that you are keeping a table like this, that one of the dimensions is going to be t. So we call this type of problems pseudo-polynomial, not exactly polynomial. Remember we have discussed about the coin changing problem. There was actually the same discussion there. That problem was called, that algorithm that is solved, we found for the problem was pseudo-polynomial. Again, there the value that you were changing was a parameter in the final time complexity. So it is another example of a pseudo-polynomial algorithm. So this specific problem, the subset sum problem, is one of those cases that
if you are writing the algorithm, it is better to write it in a top-down way than bottom-up way. Usually when we talk about dynamic programming and any recursive problem, we say that it is better to write it in a bottom-up way because you are going to get rid of all the overhead of recursive calls. But in this case, because you are going to just look for a true false answer, and it's a good chance that if you write your algorithm in a top down way, you find the answer earlier, and in the search, whenever you find it, the search will be finished. It's just like maybe you don't need to fill the whole table here, because in a top down way, we don't necessarily fill all the table. In a bottom up way, I will definitely fill all of the cells in the table, right? But in a top down way, you actually started solving the largest problem, and you solve as many sub problems as you need based on the input, whatever is the input. Maybe you are very actually lucky and you just need to solve a smaller number of sub problems. And there's a good chance in this case, in the case of subset sum problem, that you don't need to solve all of the sub problems. So this is one of the cases that you prefer to write it down in a top-down way than bottom-up. So what I have actually explained in the, in this example here, was just writing the true-false. Right, at the end, whatever is going to be this cell, the answer at this cell, this is going to be the answer of your problem, right? It's going to be true or false. Yes, I have a subset of the numbers which is equal to t, or no, there is no subset that the answer is going to be equal to t. But one thing is that not only we want to know if the answer is yes or no, we also want to have that set of numbers. How we can actually calculate, how we can find that set of items, that set of numbers, we can basically do some search over this table. If this answer is true, you can just trace it, that where this answer is coming from. You can either actually write down that where it is coming from, or you can, because basically you have only two choices, right? So for this case, there are these two choices. Look at them, and whatever is true, just go to that cell, whatever it is. So in this case, probably the answer is going to come from 15. I don't actually, I can't find it here, but anyway, whatever is the answer is coming from one of these two cases, right? Just trace those cells which are true from here, where you are getting the true, either from this case or this case, and from there where you are getting that answer in the cells, and just actually trace it back in the table, and you can find all those numbers that the summation of them is equal to 19, or t in total. So just as an exercise, try to write down this pseudocode, that search in your table and trace down and find a set of numbers that the summation of them is equal to t. So we have solved the subset sum problem. Now I'm going to actually switch to the knapsack problem. It is very, closely related to subset sum, so now we can actually think about it, that how to solve the knapsack. Remember, the knapsack problem was that I have an object. There are two numbers associated to each object, some value and some weight. I wanted to maximize the value. I wanted to take a set of those items and maximize the value while the summation of the weights is less than W. Let me give you an example for this, example of a problem. some instance of a problem. Assume W is equal to 11 and I have 5 objects. Okay, so these are the objects, these are the value associated to them and the weights associated to them. Item 1 has value 1, weight 1, item 2, value 6, weight 2, and so on. So what is going to be the optimal answer in this case? If you search and actually look at all the items, you can see that if I take the item 3 and 4, the summation of the weights is going to be equal to 11, and it is going to give me the maximum value, which is 40. So how can I actually solve this problem? One algorithm that might actually come to mind is that intuitively you would think that those objects that has higher values and lower weights are going to be preferred, right? So I can define some ratio like weight based on, the value based on weight by dividing value over weight for each object. And you can see that it is telling me that, for example, object 5 is very likely to be chosen because the weight of it is 7 and it has the highest actual value. Compared to the rest of the item, it is going to be actually having the highest value per weight ratio. Okay, so this algorithm is telling me that, okay, try to take all the items from the largest, from the maximum weight to, value to weight ratio. So by this algorithm, you are going to take the object 5, and then after you are taking 5, because the weight is 7, you only have 11 minus 7 weight remain, right? So with weight 4, you cannot take this item, you cannot take this item. These are the maximum weight per ratio, right? So it means that you cannot take this one, you cannot take this one. How about this one? Yes, I can take the item 2. So I'm going to take the item 2, and the weight is 2, so the remaining weight is 1, and then you can take this object. So in total, you are going to take 5, 2, and 1, which the summation of the weights is going to be, a summation of the values are going to be 28 plus 6 plus 1, which is going to be 35, less than the previous answer, the optimal answer that I found, right? So this is not going to give me the optimal answer. Actually, this algorithm, which is very intuitive, is going to be, when we talk about greedy algorithms, I'm going to show you that this algorithm is can find the optimal answer if you can take actually a fraction of the objects. You are not supposed to just take the object or no. This knapsack problem that we are talking about, you should take an object, or you cannot actually either take it or don't take it. You cannot take a fraction of an object. But if you could take a fraction of the objects, in that case, this algorithm is going to work, because what would happen in that case, you would take 5 and then the remaining weight is going to be 4, so you cannot actually take the next item with the maximum value per weight ratio. You cannot take all of it, right? But I'm going to take just, for example, if I have 4 kilograms remain, I'm going to just take 4 kilogram of this object 4, right? So in total, I'm going to take the maximum amount of value, because I can actually just take some fraction of the objects. So we are going to prove that this greedy algorithm works. It will be optimal if you have a fractional knapsack problem. But for the 0, 1 knapsack problem that we are going to solve here, either you take the item or you don't take it, you can't take a fraction of it, this algorithm is not going to work. It's not finding the optimal answer for me. So as you have seen, because I have two parameters associated to each object, both W and weight, and basically you are going to maximize the value, but you have another constraint over the weight, which all those numbers are completely unrelated to the values, right? There's no direct relation between value and weight. You don't know anything about that. So this problem became a more difficult problem. It is going to be very similar to the subsum problem, and the formula for that is, in fact, the recursive relation and everything will be exactly similar to the subsum problem. You would say that from the set of all n items that you have, again, either I am going to take the first item or I'm not going to take the first item, right? Remember that recursive, that search tree, that you have access to all the items from 1 to n, and the weight that you can carry is W. So either you are deciding about each object in each of these cases. You are either taking the first object, so in that case, the only set of items that remain will be from 2 to n, and how much weight remains? W minus A1. Or you are not going to take A1, so the set of objects that you are going to decide about is going to be from 2 to n again, and the weight W is not changed. This is going to be the same. So this is exactly the same search space. I mean, the type of it is exactly the same search space as you had, but the difference here is that you are not thinking about true false, you are going to maximize it. So whatever is the result here and here, you compare them and get the maximum out of it. So if you are going to take from this one, you are adding the value of A1 as well. So let's actually just write this one as a W1. Okay, and W1. So it's telling you that if you go this way, you can add the value of the first object as well. So this is going to be the maximum between these two cases. And in the left side, you also are going to add the value of that object. So this is going to be the full recursive relation. I mean, the form of the subproblems is exactly the same, that I and W prime, that I tells you that you have access to all the items from I to n. Okay, and the W prime is the weight that you can actually carry, the remaining weight. And I have two subproblems, two cases that I have to consider. Either take the value, either take the object I or don't take it. If you are taking the object I, so you are adding the value of object I as well. If you are not taking it, the weight is not going to be changed, right? If you are taking it, you have to decrease that weight from W prime, and this is the subproblem that you have to solve. Either or don't take it, and the answer. So compare these two and get the maximum. The rest, the pseudocode and everything is going to be very similar to the subsum problem. So I have written actually the complete pseudocode at the end of the slides, but try to write it yourself, then compare it to the answer that I have given at the end of the slides.